All right, and we're going to go to the last talk before the discussion section of the day, where Nav and Sridhar will be talking about cold chain comptonization in black hole coronae.
Okay, is the screen visible?
Yep, we see the screen and we hear you.
Great. Okay, so in the next 15 minutes or so, I'll be talking about what we think powers the high energy non-thermal X-ray emission observed from black holes, black hole X-ray binaries. So we have a very good idea of what a corona looks like this, but we really don't know how or what powers it, and we'll look into that now. So yeah, this is an artistic depiction of a black hole X-ray binary, and such systems, we know that they undergo events of outbursts due to certain instabilities in the accretion disk, and they exhibit very interesting changes to their observed properties. During the beginning and end of outbursts, the observed X-ray spectra are hard with a shallow power law index and a high energy non-thermal tail, as seen over here. And during the peak of an outburst, the spectra are soft with a very steep spectral index. So the left panel here, it shows the total X-ray spectra, the black curve, and its subcomponents, the dashed lines. For example, the purple one here is due to the quasi-black body X-ray emission from the accretion disk. The same soft X-ray photons from the disk with energies typically of the order of, say, a keV or less, is believed to be upscattered due to thermal comptonization by a cloud of electrons constituting the so-called corona. And these electron distribution in the corona are believed to be hot and described by a thermal Maxwellian distribution, usually. And these upscattered photons constitute the high energy non-thermal component of the observed X-ray spectrum. If the hot electrons are energizing the photons, then they must also lose their internal energies due to inverse Compton scattering. And what continually powers or supplies energy to these electrons in the corona, despite them getting cold very, very efficiently, is the puzzle that we will be, I'll try to address in this talk now. Okay, so one possibility could be that there could be magnetic reconnection happening. For example, so this is a general relativistic force-free simulation of an accretion disk that is affecting magnetic field lines. And throughout its evolution, you can see that, wait just a second, I'll go to the correct, okay, yeah, now, yeah, so throughout its evolution, you can see that due to the shearing motion of the accretion disk and the field lines anchored onto the disk, they shear across each other, and the oppositely oriented field lines come closer and they reconnect. And these magnetic reconnection events can be seen to occur, for example, in these layers here, and they happen very frequently across the corona. And these magnetic reconnection events, which happen above the disk in the corona, they give rise to these coherent magnetic structures called plasmoids. And these plasmoids are the ingredients of the cold chain comptonization that I'll be talking about here. So yeah, magnetic reconnection does happen here in, above the disk, and they have been naturally seen in both GR MHD simulations and also force-free simulations. So what we do is we perform kinetic plasma particle in cell simulations from first principles of radiative relativistic reconnection with pair as well as electron ion plasmas. This is because the exact baryon loading into the corona is a bit uncertain. So we investigate the effect of varying levels of magnetization, sigma, and also the intensity of soft photon field that comes from the accretion disk, which impinges on the coronal electrons. So sigma is the ratio of magnetic energy density to the resonance energy density, and the soft photon flux, which is responsible for the cooling of the plasma, is equivalent to, say, the m dot of an accretion disk, or here we parameterize it with this gamma critical parameter, which denotes the particle Lorentz factor for which the decelerating IC power equals the accelerating power of the reconnection electric field. So simply put, higher gamma critical, lower cooling, and vice versa. So first, let's look into the case with pair plasma. So here you see the various properties of the plasma along the reconnection layer: density, number density, magnetic energy density, the total inverse Compton power carried by the plasma in the reconnection layer, the bulk motions component to the total power and the internal motions component to the total power. So I just want to remind you that this is the reconnection layer that you saw in the earlier animation about on the force-free simulations where the plasmoids were going up. That's the one that we are simulating here. The reconnection is triggered at the center of the box, and the plasma are propelled away from x equals 0 towards the edges of the box due to magnetic tension that is pulling them away. You can already see some major differences between the strongly inverse component cooled, and weakly inverse component cooled regimes, especially in the properties of the inverse power. For strongly cooled regimes, the internal motions are strongly cooled or strongly suppressed compared to the weak cooling regimes, and therefore perhaps the bulk component can be responsible for the total inverse component power of the coronal plasma. This is already hinting at this particular physical process, and in the next few slides I will delve more deeper into it. So what you see here in the right panels is the bulk outflow momentum, gamma beta, for different levels of cooling along the simulation domain. Stronger cooling in the top panel, weaker cooling over here. The effect of cooling and the magnetization on the bulk outflow is better summarized in the left figure. So we find that the mean bulk outflow motion, the markers over here, it is barely affected by external inverse component cooling, and it remains at transrelativistic speeds for the considered magnetizations of much greater than 1 here. This is a very interesting finding because the bulk motions or the kinetic energy that they carry is not really affected by the bulk motions of the coronal plasma. It's not really affected by the soft photons hitting them, or the density of the soft photons. The error bars here, they denote the spread in the outflow distribution that you see here, the spread along the y-axis. This ordered versus disordered motion can be very important in determining the soft photon scattering by the bulk plasmoidal motions, and thus the overall Comptonized spectrum. Similar, yeah. Next here, we'll take a look into the energies of the coronal plasma particles. The internal energy, or the temperature, the blue curves of the particles, are seen not only to scale with sigma magnetization, but also that they are strongly influenced by the strength of IC cooling. For strongly radiative regime, the left part here, the particles are cooled down effectively to non-relativistic temperatures, say 5 keV or even lesser. That's the coronal temperature, to non-relativistic temperatures, which would render them incapable of engaging in thermal Compton upscattering. On the other hand, the bulk kinetic energy, the red curves, are insensitive to the inverse Compton cooling, and that its contribution to the total energy at strong cooling regime is larger than the internal energy component of the particles. So this bulk motion can, in principle, upscatter the soft photons, and that's the only way. That's the only component of the particles' energy that can upscatter photons to higher energies, even though the particles themselves have lost their thermal energies and they have cooled down.
I have in about 2 minutes.
Yeah. So another important aspect is that if you look at the bulk component, the brown spectrum here, it resembles very well Maxwellian profile. So whatever we call as the Maxwellian distribution of the electrons could as well be the bulk component of the particles' energies, and not necessarily the internal motions. So we also look into electron ion plasmas, and even here you see very similar results. But the fact is that you can attain similar results even for a very low magnetization of sigma 3 as compared to sigma 40 for paired plasmas. The bulk motions of cold electrons, even in a weakly magnetized electron ion plasma, can participate in comptonization, and that the hot ions, which do not really radiate well, they do not transfer their thermal energy to electrons. So the electrons remain hot, and the ions remain hot, and the electrons remain cold, and yet the bulk motion of the electrons can participate in Compton scattering. So with the inputs, with the first principle physically motivated inputs from the particle and cell simulations of the particles momenta, we then perform Monte Carlo radiative transfer calculations, and then we obtain an X-ray spectrum. The blue and orange ones are the observed Cygnus X1 spectra, and then we fit it with our bulk Comptonization model for different magnetization parameters, and you can see that it remarkably describes the data across more than 3 orders of magnitude. And the maroon line also suggests that perhaps the corona is multi-magnetized. There are, say, 90% of the corona has a magnetization of 10, and perhaps 10% has a magnetization of 40, which can explain the high energy tail as well. Yeah, I will leave it here with the takeaway slides. So for large soft photon flux, the particles in the corona are cooled down to non-relativistic temperatures for all sigma magnetizations. Their bulk flows, however, they remain trans-relativistic. So since the particles are cooled down, they cannot really participate in thermal Comptonization. They're cooled down to like 5 keV, so it's hard. The particle's energy spectrum is dominated by its bulk component, and it resembles very much like a 100 keV Maxwellian distribution, which we have typically is because of the particle's energies, but that's not the case. So this bulk motion of cold electrons can upscatter soft photons and produce the observed hard X-rays. And even in the presence of ions, this work, and that can help bringing down the magnetization to much, much lower values. And even in these 2 species corona, ions remain hot. They don't radiate well because of their mass, and the electrons which are cooled down can still participate in bulk Comptonization. Yeah, here's a schematic showing that. Yeah, that's it. Happy to take any questions.
All right. Let's thank Navin for the first time. Now, are there any questions? I'll start with the room. I see someone heading to the microphone.
There are questions.
Hello, it's Yuri Boat, and I would like to ask, in X-ray binaries, we know there is spectral evolution from the hot to the soft state, that the spectrum gets softer. Normally, this is explained by the evolution, for example, of the truncation radius, that when you go to the soft state, there are more soft photons from the disk, and therefore, for example, the temperature of this electron plasma goes down. But if you have bulk Comptonization, then there is no, I don't see any obvious physical mechanism that would make the spectrum softer when you increase the density of the soft photons. How you can explain this, like in this?
It's a good question. Yeah, we can do that. So here you can see that the spectrum has is very well described with a power law index of 1.5 here through this model. But this index can be made even steeper. Yeah, steeper as we go on to softer states. And this power law index is determined by 3 major parameters. One is the magnetization, of course. Number 2 is the Compton amplification factor, which is somehow related to the magnetic compactness of the corona itself. And this compactness parameter and amplification factor, they are related to the optical depth of the corona. So that is the second parameter, which can influence the spectral index. And the third parameter that can influence the spectral index is, of course, the intensity of the soft photon. Wait, I showed it somewhere. Yeah, over here. So varying the intensity of the soft photon field. Here we fix the soft photon field to a regime that is very appropriate for hard states, low hard state of with a 1% Eddington luminosity, for example. But if you increase this, cooling will happen very less efficiently and with different optical depths that will influence the magnetic compactness parameter. And we have seen in our simulations that the spectral index can also change accordingly.
All right. Phil, you have a question?
Yeah, thanks. Yeah, so some years ago, Andrea Maloney made an argument that basically because of if you take the luminosity of the corona, that you need to give for any reasonable coronal size to have a store of energy, right? Otherwise, it would just very rapidly cool down, and you just extract everything from the electrons. So I was wondering how, is that possible in this case? That do you have effectively, with the bulk motion, it act as a store so that you can tackle this problem of the energetics? So because you can't just continually reheat at the rate that you extract luminosity.
Yeah, so the electrons are not reheated. So the thing is, electrons are cooled down. The electrons get cooled down faster than. There are two heating timescales. There are two timescales of interest here. One is the inverse Compton cooling timescale, and the other one is how long do the electrons live in the system here. So if the electrons live longer in the system, they can easily get cooled down by the soft photons, and they are not going to be energized again unless and until there are some some mechanisms which we don't want to get into. So the electrons are going to get cold. They themselves are not going to Compton upscatter, but the bulk motions is where most of the energy resides, and it is in the bulk motion that that is continuously getting energized against the Compton losses, and that can upscatter the photons.
Thank you.
Unfortunately, I think there's another question in the room, but I think we need to move on to the discussion. So maybe we should ask that question on Slack. And let's thank both Navin and all of our speakers so far.
Thank you.
So Jerome, you might want to stop the recording.